In the last part of this chapter on unit commitment, we'll first briefly look at mixed integer programming approaches to unit commitment and then move on to an alternative approach to make-whole payments. So let me start by observing that commercial software for solving mixed integer programming problems has become much more capable in the last decade. And in principle, such algorithms can exactly solve problem 10.1, where we wanted to minimize our costs consisting of startup, minimum load or no load operating costs, and incremental energy costs, subject to our system constraints. And of course, the ZK, XKs had to live within our generator constraints. Writing them out explicitly, we had linear constraints relating ZK and XK, but Z was additionally required to have integer values in each of its element. X, of course, is continuous. All US ISOs now use mixed integer programming algorithms for solving unit commitment. It has basically supplanted Lagrangian relaxation for various reasons, including that it tends to get a higher quality solution. However, these mixed integer programming algorithms might be terminated before completion to optimality because solving the problem to optimality might take excessive computational effort. We will nevertheless suppose that the ISO can solve problem 10.1, this problem here, and that the minimizer is Z star, X star. We already made that assumption implicitly when we discussed Lagrangian relaxation, since we actually found the optimal commitment and dispatch by inspection, albeit guided by some of the insights from Lagrangian relaxation. So, I want to build on that and take another approach to make-whole payments. And to do that, let's start with some analysis. Recall that in the offer-based economic dispatch problem, we required that the cost function was convex. Similarly, in our unit commitment problem, we require that the incremental energy and reserves costs are convex. That is to say, for fixed Z, the cost function f, evaluated at a particular z, but thought of as a function of the remaining x variables, that function is convex. And in particular, if I plug in z equal to z star, that function would be convex. For my subsequent analysis, I'm going to need to suppose something a little stronger. I'm going to suppose that the cost function f can be extrapolated to a function that is convex on the whole of reals np times nt cross reals 2np times nt. In other words, if I now think of both z and x as continuous, I want to think of the resulting function as a continuous function of both variables. As an example, each fk would be convex if it can be expressed as a linear function of zk and xk, and if each fk is convex, then f itself would be convex. So let's consider the following problem. We're now going to not require z to be in an integer lattice, but instead we're going to add a couple of extra constraints. We'll still have the objective we saw before. We've got the constraints, system constraints and generator constraints, but we're going to add two more sets of constraints. The first set is going to be zkt is less than or equal to 0 for those generators and pricing intervals such that zkt star is equal to 0. Furthermore, for each kt such that zkt is equal to 1, we're going to require zkt to be greater than or equal to 1. Notice that this problem doesn't actually help us to solve our unit commitment problem because it presupposes we know the solution. Nevertheless, it will help us with pricing. The feasible set of problem 10.3, the one I've just defined, is a subset of the feasible set of our unit commitment problem. Furthermore, that problem is convex because we're now allowing little z to be chosen from a convex set. Each entry is constrained by the inequalities to be one particular fixed value, either 0 or 1, and we've also assumed that f is convex for fixed z, Consequently, for the particular value of z equal to z star, our feasible set, in fact, is a convex set, and the objective is convex on that feasible set. So by theorem 4.12, the first order necessary conditions are satisfied by a minimizer of this problem. The constraints on z in problem 10.3 require that z is equal to z star. In other words, we've required that the discrete variables in problem 10.3 are required to be equal to the values that we happen to know to be optimum, assuming that we could solve problem 10.1. Z star x star, furthermore, is a minimizer of problem 10.3. Why is that? Well, z star x star is clearly feasible for problem 10.3 because the only constraints that are different to problem 10.1 constraints are the constraints that effectively require z to be z star. Furthermore, z star x star is a minimizer of problem 10.1, and the feasible set of problem 10.1 is bigger than, it contains the feasible set for problem 10.3. So conceivably, since problem 10.3 has a smaller feasible set, it might have a higher minimum and a different minimizer, but since the minimizer of 10.1 is by construction feasible for 10.3, that minimizer of 10.1 is also the minimizer of 10.3. Furthermore, x star is also a minimizer of problem 10.4, where I now remove z as being a decision variable and simply plug in z star to my objective. So in problem 10.4, the discrete variables are explicitly fixed at their optimal values. As previously, let's define lambda star, mu underline star, and mu overline star to be the Lagrange multipliers on the system equality and inequality constraints and the generator lower and upper bound constraints in problem 10.3. Just an observation, previously in this chapter we used lambda star and mu star to denote the values of the dual maximizer calculated in the Lagrangian relaxation approach. The values of lambda star and mu star in 10.3 will generally be different to the values of the dual maximizer. If we look at problem 10.4, however, where we set the discrete variables to be fixed at their optimal values, we'll find, for a similar argument to the relationship between 10.1 and 10.3, that we would get the same values of Lagrange multipliers in 10.4 as 10.3. Additionally, I'm going to define a couple of extra vectors of Lagrange multipliers. Let me call them rho underline star and rho overline star. Rho underline star kt is going to be the Lagrange multiplier on the zkt is less than or equal to 0 constraint. That applies for all kt such that zkt star is 0. Similarly, p overline kt star is the Lagrange multiplier on the zkt greater than or equal to constraints. Notice that for each k and t, either zkt star is 0 or zkt star is 1. So we only enforce one or the other of these constraints, and correspondingly in these vectors, there's only going to be an entry in rho overline and rho underline. For each kt, there's only going to be an entry either in rho underline or rho overline. There are some missing entries, in other words. So we're now going to interpret these constraints to be additional system constraints. They're really applying to each generator, but for a moment I want to interpret them as additional system constraints on additional commitment commodities. So these zk's I now will interpret to be commitment commodity constraints, and we'll pay generators based on these constraints and on the associated Lagrange multipliers. This is stretching my earlier definitions and assumptions, and the reason for this is because it will form the basis of another make-whole payment rule. So we're going to define a pricing rule for both the integer and the continuous decision variables. For the continuous variables, we've seen it before. Pi xk is equal to minus ak transpose lambda star minus ck transpose mu star. For the integer variables, this is the new thing, the price paid to zk for commitment variable zk is going to be rho overline k star minus rho underline k star. Notice that zk is a vector, and indeed we'll organize the rho underline kts and rho overline kts into vectors that are appropriately numbered so that when we do this subtraction, we subtract corresponding entries. The implication is that the payment to a generator is going to consist of a payment for energy and for reserves potentially based on lambda star and mu star, and a make-whole payment, or perhaps a charge, based on rho overline k star and rho underline k star. This make-whole payment is again going to be charged as an uplift to demand. And as with the previous make-whole payment based on the maximizer of the dual, this means that we will be making payments that are different for each generator. So the prices are not anonymous. The payment to generator K depends on a Lagrange multiplier, in this case, that's explicitly associated with a generator constraint for generator K. So let's consider a Lagrange multiplier, rho overline kt star, associated corresponding to a particular constraint zkt is greater than or equal to 1. If pkt overline star is not equal to 0 and zkt equals 1, then the generator receives a contribution to its payment of pkt overline star. Similarly, if p underline kt star is not equal to 0 and zkt were equal to 1, then generator K would be charged a penalty. So this is going to encourage the generator to be committed when rho overline kt star is positive, and it's going to encourage the generator to not be committed when rho underline kt star is not equal to 0. Over a day, the total payment would be pi zk transpose zk, and just multiplying those entries together, what we would get is the sum over the pricing intervals of the day, the difference between these two entries, times zkt. And just for uniformity's sake, or well-definedness sakes, whenever zkt star is equal to 0, remember I don't have the constraint zkt is greater than or equal to 1. Nevertheless, I'll define the corresponding Lagrange multiplier to be 0, and similarly I'll define rho underline kt star to be 0 if zkt is equal to 1. So let's show that the pricing rule results in zk star and xk star being the profit maximizing commitment and dispatch decisions for generator K. In order to do that, I'm going to define another relaxed problem. I'm going to consider a relaxation of generator K's profit maximized problem that's obtained by allowing it to choose continuous values of zkt. So let me write it sk overline. All I'm going to require is that the inequality constraints be satisfied. I'm not going to require that z be integer valued. We'll call that the relaxed generator feasible operating set. And remember, I've extrapolated the cost function so that it is defined on all possible continuous values of z. Let's consider profit maximization for the relaxed profit maximization problem. So in the relaxed profit maximization problem, I'm going to pretend that zk/xk can be chosen from the relaxed feasible set, the relaxed generator feasible operating set. I'm going to pay the continuous variables based on the prices pi xk. I'm going to pay the discrete variables based on my prices rho overline k and rho underline k. And of course, profit maximization means maximizing revenues minus costs. And I've already defined the prices. This problem is a convex problem since the relaxed generator feasible operating set is convex and the objective is assumed to be convex on this feasible set. So we can apply pricing theorem 8.3 to this problem. We denote the solution of the relaxed generator profit maximization, problem 10.5, by zk double star, xk double star. We're going to interpret ax equals b, cx less than or equal to d, zkt less than or equal to 0 for all k and t such that, or t such that zkt star is equal to 0, and zkt greater than 1 for all t such that zkt is equal to zkt star is equal to 1 as system constraints. They're not really system constraints, but by interpreting them as such, we can find a useful interpretation. By theorem 8.3, if we dispatch at zk double star, xk double star, assuming it were possible, that is to say, at the solution of problem 10.5, we would obtain profits for generator K that could be no higher than the profits under the corresponding entries of the solution of the convex problem 10.3, namely zk star, xk star. That means that in fact these guys couldn't have produced a better solution. Zk star and xk star is in fact optimal for the relaxed generator profit maximization problem. But we already know that zk star, xk star is feasible for the unrelaxed profit maximization problem that has to respect integrality. In other words, the problem that requires zk, xk to be in the true feasible set and maximizes this objective. So therefore, zk star, xk star is also optimal for the unrelaxed profit maximization problem for generator K, namely 10.6. Since zk star, xk star is in S, which is contained in sk overline. In other words, we couldn't have done better in this problem when we restrict ourselves back to the original integrality requirements. We couldn't have done better than zk star, xk star because we already know that zk star, xk star minimizes this objective over the larger feasible set where we relax integrality. Zk star, xk star maximizes profits for generator K over sk overline. Since we've proved it's a maximizer of the relaxed generator profit maximization problem, zk star, xk star is inside sk, so therefore zk star, xk star also maximizes profit over sk. There couldn't have been a better point in sk. The prices, if we interpret not only lambda star and mu star, but also row overline star and row underline star, if we interpret those as prices on energy and commitment variables, then we have obtained what we can call dispatch and commitment supporting prices. There are no choices of zk, xk that would yield a higher profit to generator K than the choices zk star, xk star. Generator K would be motivated based on these prices to commit and dispatch according to zk star, xk star. There just isn't a better solution for them. So we can think of prices and make-whole payments. Prices, lambda star, mu star, make-whole payments effectively based on row underline star and row overline star as commitment supporting prices. And we'll contrast these prices with those obtained from the maximum of the dual from the Lagrangian relaxation formulation. So let's see that in an example. Let's consider the example with 100 heterogeneous generators, marginal costs that were of the form beta k is equal to 1 plus k over 100, and demand d overline equal to 303. Let's consider the first order necessary conditions for problem 10.3, where we constrain the commitment decisions with inequalities. We require the committed generators, we require zkt to be greater than or equal to 1 for the committed generators, less than or equal to 0 for the non-committed generators. Because we're only considering a single time period here, let's drop the subscript for time. So we can observe that in problem 10.3, the gradient of F76 should be equal to lambda star. That tells us that lambda star is 1.76. Furthermore, the gradient of F with respect to Z should be equal to rho overline. And we know that that's equal to 4 from the functional form in the example, and so we obtain that rho overline 76 star is 4. So in this case, the commitment supporting prices for generator 76 are an energy price of $1.76 a megawatt hour. Generator 76 is therefore marginal, together with a make-whole payment to generator 76 of $4 an hour, if it's generating. How about for generators 1 through 75? A similar analysis tells us that 0 is equal to 1 plus k over 100 minus lambda star plus mu overline k star, and 0 is equal to 4 minus 4 mu k overline star minus rho k overline star. We already know what lambda star is. Mu overline k star is the Lagrange multiplier on the maximum capacity constraint that requires xk to be less than or equal to 4zk, and plugging that information in, we find that the price should be $1.76, and there would be a make-whole payment, pk overline star, that's equal to 4 minus 4 mu k overline. Repeating that, the commitment and supporting prices for generators 1 through 75 are an energy price of lambda star equals $1.76 per megawatt hour, and a make-whole payment based on rho k overline star equal to 4 minus mu k overline star. And evaluating that based on the expression at the top here, we get 4 minus 4 lambda star minus 1 plus k over 100, which gives us 1 plus k minus 1 over 25. Given an energy price of $1.76 a megawatt hour, generators 77 through 100 will remain off, and there's no additional make-whole payment for these generators. Demand is going to have to pay for all the make-whole payment. The energy would be based on the lambda star times demand, $1.76 per megawatt hour times 303 megawatts, which would be $533.28, plus make-whole payments to generators k equal 1 through 76, given by $80.48 per hour. So the expression for generators 1 through 75 is 1 plus k minus 1 on 25. For generator 76, it's 4. So compared to the case where the dual maximizer was used to price energy and the make-whole payment was only made to generator 76, these commitment supporting prices result in a larger make-whole payment. They're paid to a larger number of market participants, but a smaller total payment by demand. In this example, the prices from problem 10.3 are actually very different to the energy prices obtained from the dual maximizer, from Lagrangian relaxation. Remember that the maximizer of the dual yielded an energy price of lambda star equal to $2.76 a megawatt hour, plus a make-whole payment of $1 an hour to generator 76 alone. On the other hand, the commitment supporting prices yielded an energy price of lambda star equal to $1.76 per megawatt hour, plus a make-whole payment of lambda k star equals 1 plus k minus 1 on 25 for each committed generator. The reason for the commitment payment to each generator is that the marginal cost of all the generators are clustered together, and the average cost of all the generators are clustered together. But for each generator, the marginal cost differs significantly from the average cost. So when we have lambda star that is matching the marginal cost of the marginal generator, we need to pay multiple generators a chunk of extra money to cover their min load cost. If the startup and minimum load costs were relatively smaller, and if there was a wider relative dispersion of marginal costs, then the difference between the two approaches would be smaller. Let's see that in an example. Let's suppose that the demand is again 303 megawatts. Suppose we've got 100 generators, generator K having cost function as before, but now the coefficient of the continuous variables is much larger. Beta K is 1 plus K. We'll see there's a much wider dispersion of marginal costs. And for each generator, the marginal cost and the average cost are not extremely different because the 4ZK term does not significantly change the average costs compared to the marginal costs. So the solution is, as we've seen before, optimal commitment of generators 1 through 75 to be at 4, producing 4, generators 76 to be producing 3, generators 77 through 100 to be off. The minimum cost, adding that all up, is 13,235, and this is the minimum of problem 10.1. So this should say generator 77 through 100 is off. We first find the value of lambda star that maximizes the dual. The dual problem, as we've seen before, find the lambda that maximizes the minimum over choices of z and x, this function. Let's suppose we set lambda so that lambda is between 2 plus 75 and 2 plus 76. For example, let's set it 77.5. We would find that generators 1 through 75 produce 4 megawatts, the rest produce nothing. Total production is 300 megawatts. If we bump it up a little bit more, then we find that total production is 304 megawatts. As previously, we cannot match supply to demand with prices. However, the maximizer of the dual occurs for lambda star equal to 78, and it's got value 13,234. Total production would be 300 or 304 megawatts. There'd still be no price where supply equals demand, but we have a small duality gap. It's very small and relatively small as a fraction of the minimum of the primal unit commitment problem. So an energy price of lambda star equals $78 a megawatt hour. Together, we still need to pay a make-whole payment of $1 per hour for generator 76 would provide for the optimal unit commitment. The demand would pay lambda star times D, 23,634, plus the make-whole payment of $1 per hour. How about commitment supporting prices? If we consider the first order necessary conditions in problem 10.3 for generator 76, we find that lambda star should be equal to 77. Furthermore, rho 76 overline star should be equal to 4. So in this case, the commitment supporting price for generator 76 is an energy price of $77 a megawatt hour and commitment payment to generator 76 of $4 per hour if it commits and generates. For generators 1 through 75, it turns out that an energy price of 77 induces each of the generators to be committed without any additional commitment payment, since the revenue for producing at xk equals 4 would be 308, and the production cost for each of the generators is less than or equal to 308. So that means that the corresponding Lagrange multiplier, rho k overline star, would be 0. So the commitment supporting prices are an energy price of $77 per megawatt hour, commitment payment to generator 76 alone of rho 76 overline star of $4. In this case, demand pays 23,331 plus 4, which adds up to 23,335. This is again less than with the dual maximizer, and however the make-whole payment is a little higher, but only slightly higher than with the dual maximizer. With a wider dispersion of marginal costs, the difference between the energy prices in the two formulations is now relatively much smaller. However, energy prices tend to vary more with commitment supporting prices in practice than with what we know would occur with the dual maximizer. Moreover, the make-whole payment is made to only one generator in both of these formulations when we have a wider dispersion of marginal costs. This case of a wider dispersion of marginal costs is likely to be typical when marginal costs have wide dispersion, almost tautologically, and when the startup and no-load costs are relatively small. So in summary, if there's a small relative difference between the two formulations, and we should ask the question, if there is a small relative difference, why bother with the complexity of the mixed integer formulation or even indeed with centralized unit commitment? Remember that the Lagrangian relaxation story basically we could implement with a relatively simple decomposed algorithm and then adjust. So why bother with centralized unit commitment? Well, the reason is related to the adjustment. It is quite ad hoc typically to adjust the solution of unit commitment. We can get a more definitively optimal solution from mixed integer programming software, and in some cases the cost of incorrect decentralized unit commitment decisions could be quite large, particularly when transmission constraints are binding. The cost of incorrect decentralized commitment decisions is an empirical question. It's in fact not been studied in a very systematic way, except for particular case studies such as the ERCOT backcast study. Why bother with the mixed integer formulation? Well, necessary heuristics in Lagrangian relaxation are very detailed and brittle, particularly with transmission constraints. The heuristics are problematic in a market setting where a particular heuristic may have significant implications for profitability or be vulnerable to strategic offers. So in practice, electricity markets in North America all now have mixed integer optimization approaches using centralized unit commitment. So we have presented a couple of different make-whole payments and some simplifications. In practice, the simplified version that I presented previously is used, and it simplified in practice approach reflects the goal of make-whole payments of ensuring that each generator is paid enough to cover its offer costs and that it commits and dispatches consistently with the optimal commitment and dispatch. All centralized unit commitment formulations, I should emphasize, require an uplift from demand. So even though I've described various alternatives, everything that involves centralized unit commitment is going to require an uplift. The simplified make-whole payment of the maximum of 0 and the costs under ISO dispatch and commitment minus the revenues under those circumstances, it can be applied to any pricing rule on energy and reserves in order to induce a particular behavior. We'd pay make-whole payments to any generator that commits and dispatches close enough or according to ZK is equal to ZK star and XK is equal to XK star. The make-whole payment would be withheld, possibly a penalty would be charged for any generator that deviates significantly from the desired commitment and dispatch. As previously mentioned, however, the simplified payment is used in practice even though it doesn't provide exactly the correct incentives. In ERCOT and other ISOs, commitment Z star and dispatch X star is calculated from the solution of the integer optimization problem 10.1 using mixed integer programming software. Energy and reserves prices are based on the Lagrange multipliers obtained from the solution of the convex problem 10.4, obtained by fixing the integer variables at their optimal values Z star. But instead of commitment supporting prices, we have a make-whole payment that's based on a daily calculation using the simplified rule. The Midwest ISO has proposed to use prices that are analogous to the prices found in Lagrangian relaxation, still using the commitment and dispatch from the solution of problem 10.1. Energy and reserves payments then based on the dual maximizer, problem 10.2, or an approximation of this problem, and then some version of a make-whole payment. In discussing make-whole payments, something that should have occurred to you is that the particular make-whole payments are applicable to particular market participants. And that brings us to the topic of anonymity of prices. An important role for prices is to inform potential entrants to the market about whether or not new entry would be profitable. Prices pi xk on system inequality and equality constraints are paid for energy and reserves, for the equality and inequality constraints, produced by everyone and anyone. We could say they are anonymous prices. They're not specific to any particular market participant. Of course, if you're at a particular bus, then you will be paid according to particular prices associated with that bus, but everyone at a particular bus will be paid the same. However, make-whole payments, including payments based on commitment supporting prices for commitment decision variables, are not anonymous. They depend on who we're paying them to. Non-anonymity is problematic. Why? Because it makes it harder for a potential entrant to determine if new entry by them would be profitable. And this is particularly the case if the make-whole payments are not disclosed publicly. And the reason is pretty clear. It's difficult for a new entrant to understand if it would be profitable to enter at the current prices given their technology. That has some implications for investment decisions. Furthermore, even if the make-whole payments are disclosed, the make-whole payments can distort investment decisions by giving a strange picture to a potential new entrant. The make-whole payments contribute to the inframarginal rents of some generators, but they're not available to everyone else. And this can have the effect of depressing the incentives for building new capacity. So far in our discussion of transmission constraints, in our discussion of unit commitment, we haven't discussed transmission constraints. However, transmission constraints can limit the dispatch decisions. So we can expand the formulation to include the transmission constraints in the system constraints. We could then consider prices based on the dual maximizer as proposed in Midwest ISO, or energy and reserve prices obtained from the solution of problem 10.4, having the variables fixed at their optimal value, or any of the other variations. In both cases, a make-whole payment may be necessary. And in practice, let me observe that transmission-constrained unit commitment can be an extremely difficult problem to solve. Let's see that with an example. We're going to consider day-ahead dispatch across 2 hours with demands 110 and 125 megawatts in the 2 hours of tomorrow. The demand in the last hour of today was 90 megawatts, and we'll assume that generator 1 was providing all of that 90 megawatts. Generator 2 was out of service at the end of today. We're going to ignore reserves, min load cost, and ramp rate constraints, and the offers are going to be specified as follows. There'll be a startup cost of $1,000 for generator 1, startup cost of $1,000 for generator 2. Generator 1 has marginal cost $25 per megawatt hour, and it sets its offer equal to its marginal cost over its operating range from 0 to 200. Generator 2 has marginal costs of 35 over its range of 0 to 50 megawatts. The generators are located in the following one-line, two-bus system, and we use the DC power flow approximation to approximate the transmission constraints. We'll assume that the transmission line has capacity 100 megawatts, and we're going to solve the transmission-constrained offer-based unit commitment, and we'll consider energy prices based on problem 10.4, where we calculate prices by fixing the integer variables at their discrete values, at their optimal values, and then calculating Lagrange multipliers on the remaining continuous problems. We'll calculate make-whole payments based on the simplified rule. So because of the transmission constraint, we're going to have to commit generator 2 and run it during both periods 1 and 2. And in fact, generator 1 can produce no more than 100 because of the transmission constraint. So that means that generator 1 is producing 90 at the end of today and 100 in each of the periods tomorrow. To meet the demand of 110 and 125, generator 2 must produce 10 and 25 megawatts respectively. We can calculate the locational marginal prices using the commitment variables fixed at their optimal values. For generator 1, it's on for all of its that period, all of the relevant pricing intervals. For generator 2, we switch it on at the beginning of interval 1. So fixing the integer variables and considering the remaining continuous problem, we'd find Lagrange multipliers on the power balance constraints of $25 a megawatt hour at bus 1, where generator 1 is located, and $35 a megawatt hour in bus 2, where generator 2 is located for periods 1 and 2. Of course, in period 0, the prices are 25. So generator 1 is marginal at bus 1, generator 2 is marginal at bus 2. Since generator 1 is already committed, and since his revenue just covers its incremental energy costs, there's no make-whole payment for generator 1. He just breaks even. Generator 2 must be started, but the revenue only just covers its incremental energy costs. Therefore, the make-whole payment to generator 2 is equal to its startup cost, which is S21 of $1,000, and that completes the example. So the final topic is day-ahead and real-time markets. As discussed in previous chapters, randomness and uncertainty is pervasive in the supply and demand of electricity, and a sequence of markets can be used to help cope with that randomness. Successive markets then compensate for and correct the forecast errors and other errors from previous markets. So for example, we have day-ahead unit commitment and dispatch that sets up what we'll explain in Chapter 11 to be financial agreements to generate a day in advance, and those commitments are made a day in advance based on forecasts or specifications of demand a day in advance. Then the real-time market deals with deviations of actual supply and demand from the day-ahead specifications. For each commodity, besides the commitment commodities, there is a corresponding day-ahead and real-time price. The day-ahead price applies to commodities bought and sold in the day-ahead market. The day-ahead market is actually a short-term forward market, and participation in the day-ahead market entails a forward financial commitment to produce or consume in real time. That financial commitment means that either the action is carried out physically or the actual deviation from the financial commitment is purchased from the real-time market at the real-time price. So payment in the real-time market applies to deviations from the day-ahead positions. To make this concrete, let me give an example. Suppose the ISO day-ahead market yields a day-ahead price of $50 a megawatt hour in a particular hour and generation of 40 megawatts by a particular generator. In the real-time market, let's suppose the real-time price is $60 a megawatt hour. Maybe demand is more than we forecast. And in that case, the generator might be asked to produce more than what it agreed to day ahead. Let's say it produces 45 megawatts. Well, then its payment consists of the sum of two things. First, the payment based on its day-ahead quantity commitment and the day-ahead price. And second, a quantity based on its deviation of its real-time quantity from the day-ahead quantity times the real-time price. So in the day-ahead, it committed to produce 40, the price was 50. In the real time, it produced an additional 45 minus 40, an additional 5 at a price of 60. The total is 2,300. Notice that that's more than what it gets from the day-ahead market alone. It's desirable that each such market, day-ahead and real-time, represents similar constraints. Otherwise, there would be a price difference between the two markets, even in the absence of randomness. There are some problems in practice, conceptually. Ancillary services such as reserves that are required in the day-ahead market are typically commitments to be available in real time. So unless there's a matching ability to buy and sell ancillary services in the real-time market, there is an asymmetry. Most markets in North America are moving to real-time ancillary services markets. ERCOT has not done that yet. When reserves are actually deployed, we need to think about the implications because they will typically be deployed in real time, not in the day-ahead market. and then what happens if a generator is paid to commit in the day ahead but doesn't actually commit. So, in this chapter, we've considered temporal issues. We formulated the unit commitment problem, we investigated the duality gap in the problem and the implications for commitment supporting prices, we briefly considered day ahead and real-time markets, and we considered reserves.